Quantum fields exist at every point in space, but a universe from nothing is mathematically impossible. The quantum vacuum, the lowest energy state of quantum fields, is not empty. It contains zero-point energy, virtual particle-antiparticle pairs governed by the Heisenberg uncertainty principle, and measurable phenomena like the Casimir effect, an attractive force between uncharged parallel plates arising from the alteration of vacuum modes. The Big Bang, the hot, dense state at the origin of the observable universe approximately 13.8 billion years ago, is the standard cosmological starting point. But it does not describe a creation from nothing. Cosmic inflation, the hypothesized exponential expansion of space driven by vacuum energy, explains the homogeneity and flatness measured by the Planck satellite. But it requires pre-existing quantum fields and the laws of general relativity. And the fine-tuning of physical constants, the cosmological constant at 6 × 10⁻27 kilograms per cubic meter, the fine structure constant at approximately 1/137, raises questions that physics describes but cannot answer. This fine-tuning points to what philosophers call the anthropic principle, the observation that the universe's properties appear precisely calibrated for the existence of observers. The evidence, when examined honestly, points in one direction, and it is not toward nothing. What follows is a forensic examination of the claims of Lawrence Krauss and Stephen Hawking, the equations and the evidence. By the end of this video, you will understand what the quantum vacuum actually is and why it is not nothing by any definition that respects the word. You will understand why the claims of Krauss and Hawking that the universe arose from nothing depend entirely on redefining nothing as a pre-existing quantum vacuum with fields, energy, and physical laws. You will understand the criticisms of George Ellis and David Albert, physicists and philosophers who identified the structural flaw in these claims. You will understand the equations, the Friedmann equation, the Heisenberg uncertainty relation, the zero-point energy formula, and what they require as inputs. You will understand why attempts at quantum gravity theories, from string theory to loop quantum gravity, still cannot explain the origin of the mathematical framework itself. And you will understand the limits of science itself. Physics can describe how the universe operates, but it cannot answer why anything exists rather than nothing. That question demands an answer that lies beyond physics. And the evidence, as we will see, demands a specific kind of answer. If this channel is the kind of content you return to, consider subscribing. There is no algorithm shortcut for depth. Let us examine the evidence. The quantum vacuum is the lowest energy state of a quantum field. This definition sounds like it describes emptiness. It does not. In quantum field theory, the mathematical framework that underpins the standard model of particle physics and describes the behavior of all known subatomic particles and forces, every fundamental field is quantized. The electromagnetic field, the electron field, the Higgs field, the quark fields, the neutrino fields, the gluon fields. Each is a quantum field that permeates all of space. At every point in space, each field has a ground state, a minimum energy configuration that cannot be reduced further. That minimum is not zero. This is one of the most counterintuitive results in all of physics. Classical physics would suggest that the lowest energy state of a system is zero energy, that nothing happening means zero energy. Quantum mechanics says otherwise. The energy of a quantum harmonic oscillator, the simplest model for a single mode of a quantum field, in its ground state is E sub min equals 1/2 h bar omega. E sub min is the minimum energy. H bar is the reduced Planck constant, approximately 1.055 times 10 to the negative 34 joule seconds, or approximately 6.582 times 10 to the negative 16 electron volt seconds. Omega is the angular frequency of that particular oscillator mode, 1/2 h bar omega, not zero. The ground state has energy. This is the zero-point energy, the energy that remains even when every particle has been removed, every thermal fluctuation has been cooled away, every possible excitation has been eliminated. The quantum vacuum is what remains when you have taken everything away that can be taken. And what remains is not nothing. The origin of zero-point energy traces to the earliest days of quantum theory. In 1911, Max Planck, working on the theory of black body radiation, introduced the concept of zero-point energy, the idea that oscillators retain a baseline energy even at absolute zero temperature. The Heisenberg uncertainty principle, formulated in 1927, provides the deeper explanation. The position and momentum of a quantum particle cannot both be precisely defined simultaneously. Delta x times delta p is greater than or equal to h bar over 2. An oscillator at rest would have zero uncertainty in both position and momentum, which violates the uncertainty principle. Therefore, the oscillator must always retain some residual motion, some residual energy, the zero-point energy of 1/2 h bar omega. This is not a theoretical convenience. It is a mathematical consequence of the foundational axioms of quantum mechanics, and it applies to every mode of every quantum field at every point in space. Now consider the implications. Space contains an infinite number of field modes. Each frequency, each polarization, each direction of propagation contributes a mode. Each mode carries a minimum energy of 1/2 h bar omega. Summing over all modes yields, formally, an infinite total vacuum energy. This is not a small problem. It is one of the deepest puzzles in theoretical physics, the vacuum energy divergence. In practice, physicists handle this through a procedure called renormalization, subtracting infinities in a controlled way that allows finite, testable predictions to be extracted. The Casimir effect, the Lamb shift, and the anomalous magnetic moment of the electron are all calculated using renormalized vacuum energy, and all agree with experiment to extraordinary precision. The vacuum energy is real. Its effects are measurable. The mathematical machinery to handle it is well developed, if not fully understood at the deepest level. Virtual particles, particle-antiparticle pairs that appear and annihilate within the constraints of the Heisenberg uncertainty relation, are another manifestation of the quantum vacuum's structure. The energy-time uncertainty relation states that delta E times delta T is greater than or equal to h bar over 2. This allows brief energy fluctuations. A non-zero energy excursion can occur for a sufficiently short time. An electron-positron pair with a combined mass energy of approximately 1.022 mega-electron volts can appear from the vacuum for a duration of approximately 10 to the negative 21 seconds before annihilating. These are not freely created from literally nothing. They are excitations of pre-existing electron and positron fields, governed by pre-existing quantum electrodynamics, constrained by pre-existing conservation laws for charge, lepton number, and other quantum numbers. Virtual particles occur within a framework. They presuppose that framework. They are processes in a system, not creations from non-existence. The Lamb shift, measured by Willis-Lamb in 1947, provided early experimental confirmation of vacuum effects. The shift is a small energy difference between two states of hydrogen, the two s sub 1/2 and two p sub 1/2 levels, that should be degenerate according to the Dirac equation. The difference arises from the interaction of the electron with the fluctuating electromagnetic field of the vacuum, with virtual photons that briefly appear and disappear, altering the effective potential that the electron experiences. The Lamb shift was one of the first precision tests of quantum electrodynamics and confirmed that the vacuum has measurable physical effects on atomic energy levels. Sean Carroll, the American theoretical physicist, summarized the situation. All forms of energy gravitate, including vacuum energy. The vacuum is infused with the potential to be anything. The quantum vacuum is not absence. It is potential. It is structure. It is the baseline state of a system that can be excited into particles, radiation, and complex configurations. But it is a state of something, not a state of nothing. The consequences are not theoretical, they are measured. In 1948, Hendrik Casimir predicted that the zero-point energy of the electromagnetic field would produce a measurable force between two uncharged parallel conducting plates placed in vacuum. The plates restrict the field modes between them. Only certain wavelengths fit in the gap, while the field outside has no such restriction. The energy density between the plates differs from the energy density outside, producing an attractive force. In 1997, Steve Lamoureux at the University of Washington directly measured the Casimir force. At a plate separation of 1 micrometer, 1/1,000,000th of a meter, approximately 3.94 times 10 to the negative 5 inches, the force per unit area is approximately 1.3 times 10 to the negative 7 newtons per square meter. Small, but real, measured, and arising from vacuum energy. If the space between those plates were truly nothing, no fields, no energy, no physical structure, there would be no force. The Casimir effect is empirical proof that the vacuum is not nothing. Think about that. A force between uncharged plates in empty space, predicted from the mathematics of vacuum energy, confirmed by experiment 49 years later. The vacuum pushes. It has pressure. It has measurable energy. Whatever this is, it is not nothing. It is a physical state with properties, dynamics, and laws. Calling it nothing is not a discovery. It is a redefinition. This brings us to the first claim that requires examination, and to the physicist who popularized it most aggressively. Lawrence Krauss, born 1954, American theoretical physicist and cosmologist, professor at Arizona State University, published A Universe from Nothing in 2012. The book became a bestseller and a touchstone of popular atheism. Krauss's argument, stripped to its essentials, goes like this. The quantum vacuum fluctuates. These fluctuations, governed by the Heisenberg uncertainty principle, can produce particles from nothing. If the total energy of the universe is zero, positive mass energy balanced by negative gravitational potential energy, then the entire universe could have appeared as a vacuum quantum fluctuation without violating energy conservation. No creator needed, no external cause. The universe, in Krauss's framing, is the ultimate free lunch. Krauss stated his position explicitly. Nothing is every bit as physical as something, especially if defined as the absence of something. Read that sentence carefully. Nothing is every bit as physical as something. If nothing is physical, then it has properties. If it has properties, it is not nothing. Krauss has defined nothing in a way that includes fields, energy, space-time, and the laws of quantum mechanics. He has then demonstrated that this rich, structured nothing can fluctuate and produce particles. The demonstration may be correct. The labeling is not. What Krauss calls nothing is, by any rigorous standard, something. The idea did not originate with Krauss. In 1973, Edward Tryon, an American physicist at Hunter College, proposed the zero-energy universe hypothesis. The universe could appear as a vacuum quantum fluctuation because its total energy, positive mass energy plus negative gravitational potential energy, could sum to zero. Tryon's proposal was the first technical version of the universe from nothing idea in the physics literature. It was published in Nature and was taken seriously as a conceptual framework. But Tryon's proposal, like Krauss's later popularization, requires a vacuum to fluctuate in. It requires quantum mechanics to define what a fluctuation is. It requires gravity to define gravitational potential energy. The fluctuation occurs within a pre-existing framework. It does not create the framework. Krauss went further than Tryon in his public claims. In debates and lectures, Krauss argued not merely that physics could describe a universe arising from a vacuum, but that physics had explained away the need for a creator. This is where the argument crosses from physics into philosophy, and where the examination must become precise. Let us examine this claim carefully. Krauss's nothing is the quantum vacuum, a state with fields, with zero-point energy, with virtual fluctuations, with the laws of quantum field theory and general relativity fully operative. His nothing has the Heisenberg uncertainty principle in force. His nothing has space-time. His nothing has a mathematical structure that makes fluctuations possible. Differential equations, boundary conditions, conservation laws, even if modified by general relativity. By any rigorous definition, philosophical, scientific, or common sense, this is not nothing. This is something. Krauss has not shown that something comes from nothing. He has shown at most that something comes from something else, namely from a pre-existing quantum vacuum governed by pre-existing laws. The achievement is real, the labeling is dishonest. The dishonesty is not in the physics. The physics of vacuum fluctuations is well established. Virtual particles are real within the framework of quantum field theory. The Casimir effect is measured. The Lamb shift is measured. The zero-energy universe hypothesis is a legitimate theoretical construct. The dishonesty is in the word nothing, in the claim that these well-understood physical processes within a well-understood physical framework constitute creation from nothing. They do not. They constitute processes within something. And the something, the fields, the laws, the space-time, the mathematical structure, is precisely what requires explanation. John Horgan, science journalist and author, noted that these theories take some arrangement of fields as given and describe processes like virtual particles appearing, but none of these poppings amount to anything even remotely in the neighborhood of a creation from nothing. Horgan's observation is the same as Albert's and Ellis's. The physics assumes a starting point. The starting point is not nothing. The physics then describes what happens within that starting point. The question of why the starting point exists is not addressed. George Ellis, the South African cosmologist, co-author with Stephen Hawking of The Large-Scale Structure of Space-Time, identified this flaw directly. Ellis called Krauss's claims untested speculative theories. He stated, he does not explain why the pre-existing fields should have existed at all. And Krauss does not address why the laws of physics exist. These are not rhetorical objections. They are structural. Krauss's entire argument presupposes the existence of quantum fields and the laws that govern them. He then demonstrates how fluctuations within those fields could, in principle, produce structures. But the argument does not, cannot, explain why the fields and laws exist. It explains how to get something from something. It does not explain how to get something from nothing. David Albert, the American philosopher of physics, holding a PhD in theoretical physics, wrote in a New York Times review that quantum field vacua are particular arrangements of elementary physical stuff, and that none of these poppings amount to anything even remotely in the neighborhood of a creation from nothing. Albert's point is precise. The vacuum is a physical state. It has properties. It obeys equations. It is something. Calling it nothing is a linguistic maneuver, not a physical discovery. The prosecution against Krauss's argument is complete on its own terms. But let us state the verdict explicitly. The claim, the universe came from nothing, fails, because the nothing invoked is not nothing. It is a quantum vacuum, the lowest energy state of a pre-existing field system, governed by pre-existing laws, describable by pre-existing equations. True nothing, absolute nothing, has no fields, no energy, no laws, no space-time, no mathematical structure, no potential for fluctuation. From true nothing, nothing comes. 0 plus 0 equals 0. The universe exists. Therefore, something has always existed. The question is not whether something eternal exists. The question is what that something is, and whether it is unconscious, purposeless matter or an intelligent, powerful creator. The evidence, as we will examine, points one direction. This brings us to Stephen Hawking, and to a claim that undermines itself in its own sentence. Stephen Hawking, born 1942, died 2018, British theoretical physicist, Lucasian Professor of Mathematics at Cambridge, was one of the most influential physicists of the 20th century. His contributions to cosmology and theoretical physics are extensive. Singularity theorems with Roger Penrose, demonstrating that general relativity predicts singularities under broad conditions. Hawking radiation, the prediction in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. The no boundary proposal with James Hartle, and extensive work on black hole thermodynamics. Hawking's scientific work is not in question. His philosophical claims about the origin of the universe are. In The Grand Design, published in 2010, Hawking wrote, "Because there is a law, such as gravity, the universe can and will create itself from nothing." This sentence has been widely quoted, widely celebrated in atheist circles, and widely criticized by philosophers and theologians. Let us examine it with precision. Because there is a law such as gravity. The sentence begins with a conditional, because something exists. That something is a law, gravity, not an accidental, arbitrary, or contingent feature of reality. A law, a mathematical structure described by the Einstein field equations, requiring a metric tensor, a 4x4 symmetric tensor with 10 independent components, a stress-energy tensor, describing the distribution of matter and energy, the gravitational constant, g, approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared, the speed of light, c, 299,792 kilometers per second, approximately 186,282 miles per second, and the full apparatus of differential geometry on a pseudo-Riemannian manifold. This is not nothing. This is an extraordinarily rich, structured mathematical framework. Hawking's sentence assumes this framework exists, and then claims the universe creates itself from nothing within it. The self-contradiction is explicit. The sentence says, because X exists, Y can come from nothing. But X is something. If the creation of Y requires X, then Y did not come from nothing. It came from X. Hawking's claim is logically equivalent to saying, because there are ingredients in the kitchen, the meal cooked itself from nothing. The meal required ingredients. The universe, in Hawking's own formulation, required a law such as gravity. The nothing in Hawking's claim is not nothing. It is a vacuum state governed by gravity, a specific physical configuration with specific properties described by specific equations. Hawking's Hawking radiation provides another instructive case. The Schwarzschild radius of a black hole, the radius of the event horizon, is R sub s equals 2gm over c squared. R sub s is the Schwarzschild radius. G is the gravitational constant. M is the black hole's mass. C is the speed of light. For a black hole of 1 solar mass, approximately 2 times 10 to the 30 kilograms, the Schwarzschild radius is approximately 2.95 kilometers, or approximately 1.83 miles. Hawking radiation describes thermal emission from this horizon, a temperature inversely proportional to the mass, roughly 6 times 10 to the negative 8 Kelvin for a solar mass black hole. The radiation is extraordinarily faint, far below any current detection threshold. Hawking radiation is popularly described as virtual particle pairs popping from nothing at the event horizon, with one falling in and one escaping. This description is ubiquitous in popular science. It is also misleading. Hawking's original derivation does not invoke literal pair production at the horizon. It describes the Bogoliubov transformation, a mathematical operation that relates the vacuum state defined by an observer far from the black hole to the vacuum state defined by an observer near the horizon. The two observers disagree on what constitutes empty space, because they are in different gravitational environments. What one observer calls a vacuum, the other observes as a thermal bath of particles. This is a consequence of quantum fields on curved spacetime, fields that already exist, governed by laws that already hold, structured by a geometry that already has a specific metric. Hawking radiation is a quantum field effect. It is not creation from nothing. It is a process within something. The Hartle-Hawking no-boundary proposal, developed in 1983, suggests that the universe has no initial boundary in time. In the mathematical formulation, the early universe is described by a Euclidean geometry, a geometry where time is replaced by an imaginary coordinate, smoothing the singularity into a rounded cap, like the south pole of a sphere. There is no edge. There is no boundary. There is no moment of creation. The universe simply is, finite but without a boundary in the Euclidean formulation. The proposal is a quantum cosmology model. It specifies a wave function of the universe using a path integral over compact Euclidean geometries. It is mathematically elegant. The no-boundary proposal, though, does not explain the existence of the framework within which it operates. The path integral requires a space of geometries to integrate over. The wave function requires the formalism of quantum mechanics. The Euclidean action requires a Lagrangian, which requires fields and their interactions. The no-boundary proposal removes the singularity, the sharp boundary at t equals 0. It does not remove the framework. It does not explain why quantum mechanics holds. It does not explain why the Lagrangian has the form it does. It does not explain why there is a wave function at all. The proposal is a specific quantum cosmological model, sophisticated, precise, and entirely dependent on the pre-existence of the laws of physics. Alexander Vilenkin's tunneling from nothing proposal, published in 1982, is perhaps the most philosophically ambitious of the quantum cosmology models. Vilenkin proposed that the universe could quantum tunnel from a state of literally nothing, no space, no time, no matter, into a de Sitter state, an exponentially expanding inflationary universe. The tunneling probability is calculated using the tools of quantum gravity. The Wheeler-DeWitt equation, which is the quantum mechanical analogue of the Einstein field equations, applied to the universe as a whole. Vilenkin's nothing is not philosophically rigorous nothing. His nothing is a state described by quantum gravity boundary conditions, conditions that specify the amplitude for tunneling from a zero-radius universe to a finite-radius universe. The boundary conditions are mathematical objects. They exist within the framework of quantum gravity. They presuppose the Wheeler-DeWitt equation, which presupposes quantum mechanics and general relativity. The tunneling requires a tunneling probability, which requires a wave function, which requires a Hilbert space, which requires the mathematical framework of quantum theory. Vilenkin's model is a theoretical construction within quantum cosmology. It does not derive quantum cosmology from nothing. It applies quantum cosmology to the question of how a universe could nucleate, and finds a mathematical answer within the pre-existing framework. The framework itself remains unexplained. What would you conclude from this evidence if you followed it honestly? Every model, Krauss's vacuum fluctuation, Hawking's self-creation, Hartle-Hawking's no boundary, Vilenkin's tunneling, assumes a framework, fields, laws, space-time, mathematical structure. Not one of them derives the framework from nothing. The nothing, in each case, is a technical term for a specific physical state within a pre-existing system. True nothing, philosophically rigorous nothing, does not fluctuate, does not tunnel, does not nucleate. It has no properties. It obeys no laws. From it, nothing follows. This brings us to the equations, and to what they demand as inputs. These are not abstract formulae taught in classrooms and forgotten. These are the mathematical descriptions of reality itself, the equations that, when solved with the right inputs, predict the expansion of the universe, the formation of galaxies, the temperature of the cosmic microwave background, and the acceleration of distant supernovae. Each of them is confirmed by observation. Each of them requires something to exist. The Friedmann equation describes the expansion of the universe. For a flat universe, one with zero spatial curvature as measured by the Planck satellite to the precision of 0.2%, the equation is h squared equals 8 pi g over 3 times rho plus lambda over 3. H is the Hubble parameter, the rate at which the universe is expanding at a given time, measured in kilometers per second per megaparsec. G is Newton's gravitational constant, approximately 6.674 times 10 to the negative 11 Newton meters squared per kilogram squared, the constant that determines the strength of gravitational attraction between masses. Rho is the total energy density, the energy per unit volume from all sources: normal matter, dark matter, radiation, neutrinos. Lambda is the cosmological constant, the parameter representing vacuum energy density, the energy of empty space. The Friedmann equation was derived by Alexander Friedmann in 1922 from Einstein's field equations of general relativity, applied to a homogeneous isotropic universe. It was independently derived by Georges Lemaitre in 1927. The equation is the foundation of modern cosmology. Every cosmological observation, CMB measurements, galaxy surveys, supernova distances, baryon acoustic oscillations, is interpreted through the Friedmann equation. It is not optional. It is not approximate. It is the master equation of the expanding universe. Every term on its right-hand side is something. Rho, the energy density, requires matter, radiation, or fields to be non-zero. If there is no matter, no radiation, no fields, then rho equals 0, and the only driver of expansion is lambda. Lambda, the cosmological constant, requires vacuum energy. If there is no vacuum, no space-time, no fields, then lambda is undefined, because there is no space in which vacuum energy could exist. G, the gravitational constant, requires a theory of gravity, general relativity, the Einstein field equations, the entire framework of Riemannian geometry on a Lorentzian manifold. If there is no gravity, no space-time, no metric, then G is meaningless. And H, the Hubble parameter, requires the concept of expansion, which requires space-time, which requires a metric, which requires the mathematical framework of differential geometry. If there is nothing, truly nothing, there is no H, no rho, no lambda, no G, no equation. The Friedmann equation is not a creation mechanism. It is a description of dynamics within a framework. Remove the framework, and the equation does not exist. The Hubble constant, the present-day value of H, is approximately 67.6 kilometers per second per megaparsec, as measured by the Planck satellite from the cosmic microwave background. An alternative measurement, using Type 1a supernovae and Cepheid variable stars, calibrated by the SH0ES team, yields approximately 73 kilometers per second per megaparsec. The discrepancy, approximately 10%, at a statistical significance of roughly 4 to 5 sigma, is the Hubble tension, one of the most actively investigated problems in modern cosmology. Whether the tension reflects a systematic error in one or both measurements, or new physics beyond the standard model, is unknown. But even the higher value implies an expanding universe with a finite age, a hot, dense past, and an origin event. The Hubble law itself, V equals h sub 0 times d, is the empirical relationship discovered by Edwin Hubble in 1929. V is the recession velocity of a galaxy. H sub 0 is the Hubble constant. D is the distance. The law is linear. Galaxies twice as far away recede twice as fast. At 1 megaparsec, 3.26 million light-years, approximately 1.92 times 10 to the 19 miles, a galaxy recedes at 67.6 kilometers per second, approximately 42 miles per second. At 10 megaparsecs, the recession velocity is 676 kilometers per second. At 100 megaparsecs, 326 million light-years, the recession velocity is 6,760 kilometers per second, approximately 2.3% of the speed of light. The Hubble law is the first observational evidence that the universe is expanding, the first empirical indication that the cosmos has a history, a direction, and a beginning. But the law assumes space-time, distances, velocities, and the framework of general relativity. It does not explain why space-time exists. It describes what space-time does. It tells us the universe is expanding. It does not tell us why there is a universe to expand. The Heisenberg uncertainty principle, delta E times delta T is greater than or equal to h bar over 2, is invoked in universe from nothing arguments as the mechanism that allows energy to appear from nothing for brief periods. Werner Heisenberg formulated this principle in 1927, and it is one of the foundational results of quantum mechanics. The principle states that energy and time cannot both be precisely defined simultaneously. A measurement of energy with uncertainty, delta E, requires a time interval, delta T, such that the product of the two is at least h bar over 2. For short times, large energy uncertainties are permitted. For long times, energy is well defined. This principle is the formal basis for virtual particle production. An electron-positron pair with a combined mass energy of approximately 1.022 mega-electron volts can appear from the vacuum for a duration of approximately 10 to the negative 21 seconds. A proton-antiproton pair requires more energy, approximately 1.876 giga-electron volts, and can exist for an even shorter time. These virtual pairs are not freely created from nothing. They are permitted fluctuations within a pre-existing quantum field, constrained by the uncertainty relation, and they annihilate before the energy loan becomes permanent. The pairs are real in the sense that their effects are measurable. The Lamb shift, the anomalous magnetic moment of the electron, and the Casimir effect all depend on virtual particle contributions. But they occur within a framework that already exists: quantum electrodynamics, the electron and positron fields, the laws of conservation for charge and lepton number. The universe from nothing argument attempts to extend this mechanism to cosmological scales. The reasoning goes, if the uncertainty principle allows brief energy fluctuations, perhaps a sufficiently large fluctuation at the energy scale of cosmic inflation, approximately 10 to the 16 GeV, could produce an entire universe. But examine the numbers. A fluctuation of 10 to the 16 GeV would be permitted for a time of approximately 10 to the negative 41 seconds, far shorter than the Planck time of approximately 5.39 times 10 to the negative 44 seconds. Wait, that arithmetic suggests the fluctuation could last longer than the Planck time. But the energy required for a universe-scale fluctuation is not 10 to the 16 giga-electron volts. It is vastly larger. The total mass energy of the observable universe corresponds to approximately 10 to the 79 giga-electron volts. A fluctuation of this magnitude would be permitted for approximately 10 to the negative 103 seconds, a duration so short that it is physically meaningless, far below any timescale on which inflation or expansion could operate. The probability of such a fluctuation, computed from the uncertainty relation, is effectively zero. Even if the probability were non-zero, the fluctuation occurs within a pre-existing quantum framework. The uncertainty principle is a statement within quantum mechanics. It requires energy as a defined quantity. It requires time as a parameter. It requires h bar, the reduced Planck constant, as a physical constant with a specific value, 1.055 times 10 to the negative 34 joule-seconds. It requires the mathematical framework of Hilbert spaces, operators, and commutation relations. Remove the framework, and the principle has no meaning. It cannot operate in the absence of the system that defines it. The uncertainty principle is not a magic wand that conjures existence from non-existence. It is a constraint, a mathematical relationship between energy and time within a pre-existing physical system. Using it to explain the origin of the system is circular. The principle presupposes the system whose origin it is supposed to explain. I return to this point often, not for comfort, for clarity. The uncertainty principle describes how something behaves. It does not explain why something exists. The equations are precise, the calculations are rigorous, and the conclusion is inescapable. The uncertainty principle cannot bootstrap a universe from nothing, because nothing does not have an uncertainty principle. Nothing does not fluctuate. Einstein's mass-energy equivalence, E equals mc squared, relates mass and energy through the speed of light, 299,792 kilometers per second, approximately 186,282 miles per second. Albert Einstein published this relationship in 1905 as a consequence of special relativity. The equation is among the most famous in physics, and its implications are total. Any mass has an equivalent energy, and any energy has an equivalent mass. The total mass of the observable universe is estimated at roughly 1.5 times 10 to the 53 kilograms, approximately 2.5 times 10 to the 22 solar masses, or approximately 8.3 times 10 to the 52 pounds. The corresponding energy via E equals mc squared is of order 10 to the 70 joules, a number so large that no everyday analogy captures it. For comparison, the total energy output of the Sun over its entire 10 billion year main sequence lifetime is approximately 1.2 times 10 to the 44 joules, roughly 10 to the 26 times less than the mass energy of the observable universe. Edward Tryon, born 1940, American physicist at Hunter College in New York, proposed in 1973 that this vast positive mass energy might be exactly balanced by negative gravitational potential energy. The gravitational potential energy of a uniform sphere of mass m and radius r is approximately negative 3/5 gm squared over r. If this negative contribution precisely cancels the positive mass energy, the total energy of the universe is zero. The zero-energy universe hypothesis. Tryon's proposal was the first technical formulation of the universe from nothing idea in the physics literature, published in Nature nearly 4 decades before Krauss's popularization. The idea has a certain elegance. If the total energy is zero, the universe does not violate energy conservation by existing. The positive and negative contributions cancel exactly. The universe is, in this framing, an elaborate zero. a vast, structured, fine-tuned arrangement of matter and gravity that sums, in total, to nothing. The elegance, though, is misleading. Even if the bookkeeping works, even if the total energy sums to zero, the accounting requires entries. It requires mass energy on one side, protons, neutrons, electrons, photons, dark matter, neutrinos. It requires gravitational potential energy on the other, which requires the gravitational field, the gravitational constant g, and the space-time metric that defines distances. It requires the laws of general relativity to relate the two. The zero-energy universe hypothesis removes the energy demand. It does not remove the existence demand. A zero-sum bank statement still requires a bank, a ledger, a currency, and the rules of arithmetic. The framework that makes the zero-sum possible is precisely the framework that requires explanation. Tryon's insight is real. The universe may have zero total energy, but zero total energy is a property of something, not of nothing. The something, fields, laws, space-time, constants, remains unexplained. This brings us to the conservation of energy itself, and to a subtlety that universe from nothing arguments exploit. In ordinary physics, in laboratories, in engineering, in everyday experience, energy conservation is absolute. Energy cannot be created or destroyed in a closed system. This is Noether's theorem applied to time translation symmetry. If the laws of physics do not change over time, energy is conserved. But in general relativity, in the physics of expanding space-time, global energy conservation is subtle and, in some formulations, does not hold. The total energy of a non-static space-time need not be constant. Energy can be created by the expansion of space itself. The cosmological constant drives the creation of vacuum energy as space expands, without violating any local conservation law. This subtlety is real. It is well understood within general relativity, and it is exploited by universe from nothing arguments. If global energy conservation does not hold in an expanding universe, then perhaps the universe's existence does not violate conservation. But the subtlety operates within the framework of general relativity. It requires general relativity to exist. It requires space-time to be dynamic. It requires the Einstein field equations to hold. It requires the cosmological constant to have a specific value. The loophole in energy conservation is a feature of the framework, not an escape from the need for the framework. Even if the universe's total energy is zero or undefined, the framework that defines energy, space-time, and conservation must exist. The loophole does not eliminate the need for a cause. It eliminates the need for a specific type of energy input within an already existing system. The system itself remains unexplained. The cosmological constant relation connects vacuum energy to the cosmological constant in Einstein's equations. Rho sub lambda equals lambda c squared over 8 pi g. The observed vacuum energy density from Planck data is approximately 6 × 10⁻27 kilograms per cubic meter, roughly a few hydrogen atoms of mass equivalent per cubic meter. In energy units, approximately 5 giga-electron-volts per cubic meter. This dark energy comprises 68% of the universe's total energy density. quantum field theory, summing zero-point energies of all field modes, naively predicts 10 to the 113 joules per cubic meter. The observed value is 120 orders of magnitude smaller. Before I continue, consider what this means. Take a moment. 120 orders of magnitude. The largest discrepancy between theoretical prediction and experimental measurement in the history of physics. The number 10 to the 120 is not a number the human mind can visualize. If you wrote a 1 followed by 120 zeros, the number would span roughly 40 meters of paper at standard font size. If every atom in the observable universe, roughly 10 to the 80 atoms, each contained another universe of 10 to the 80 atoms, you would have 10 to the 160 atoms. The discrepancy of 10 to the 120 is smaller than that total, but it is in the same neighborhood of incomprehensibility. This is the scale of the puzzle. If the vacuum energy density were the natural value predicted by quantum field theory, 10 to the 113 joules per cubic meter, space-time would curve so violently that the universe would have expanded or collapsed on a timescale of roughly 10 to the negative 44 seconds. No atoms, no molecules, no stars, no galaxies, no chemistry, no structure of any kind. The universe would be a featureless, exponentially expanding void, or a collapsed singularity. Neither permits complexity. If the vacuum energy density were precisely zero, if the cosmological constant were exactly lambda equals 0, the universe would not accelerate in its expansion. The expansion would gradually decelerate under the gravitational attraction of matter. Galaxies would still form, stars would still burn, chemistry would proceed, but the long-term future of the universe would be different, and the specific conditions that produce the universe we observe, including the rate of structure formation, the distribution of galaxies, and the cosmic web of filaments and voids, depend on the actual non-zero value of lambda. The observed value is neither the enormous natural prediction nor zero. It is 6 times 10 to the negative 27 kilograms per cubic meter, a specific, extraordinarily small, non-zero number. This number, from a landscape of possibilities spanning at least 120 orders of magnitude, permits the formation of galaxies, stars, heavy elements, planets, and the conditions that allow complex chemistry. This is what physicists call the fine-tuning of the cosmological constant. This exemplifies the anthropic principle. The universe's properties appear precisely calibrated for observers. It is not a metaphor. It is a quantitative statement about the sensitivity of the universe's large-scale structure to a single parameter. The cosmological constant is not the only fine-tuned parameter. The fine structure constant, alpha, approximately 1 over 137.036, determines the strength of the electromagnetic interaction. It controls the stability of atoms, the rates of chemical reactions, the properties of materials, and the behavior of light. If alpha were significantly larger, atomic nuclei would repel each other so strongly that no stable atoms beyond hydrogen could form. If alpha were significantly smaller, electrons would not be bound tightly enough to nuclei for complex chemistry. The value 1/137 is not derived from any known theory. It is measured. It is a brute fact. And it is a brute fact that permits the existence of atoms, molecules, and chemistry. The gravitational constant, the mass of the proton, the mass of the electron, the strong nuclear force coupling constant, the ratio of electromagnetic to gravitational force, each of these parameters has a measured value that, if altered by modest amounts, would produce a universe dramatically different from the one we observe. Some combinations would produce universes with no stable nuclei. Others would produce universes with no stars. Others would produce universes that expand too rapidly for gravitational condensation to produce structure. The specific combination of constants we observe is a narrow window in a vast landscape of alternatives, a window that permits complexity, structure, and the conditions for conscious observation. This is the part that stays with me. Not the scale, the precision. Precision requires decision. A radio dial with 10 to the 120 possible settings tuned to one specific frequency that produces a coherent signal was not tuned by accident. A combination lock with a landscape of possibilities spanning 120 orders of magnitude, set to the one combination that opens the door to structure and complexity, was not set by chance. The fine-tuning of the cosmological constant is not a small coincidence. It is not a modest improbability. It is a precision of 1 part in 10 to the 120. And the materialist has no explanation for it that survives scrutiny. The materialist response to the fine-tuning of the cosmological constant and to the fine-tuning of other constants, like the fine structure constant, alpha approximately equals 1/137, is the multiverse. Let us examine whether this response holds. The multiverse theory proposes that our universe is one of an infinite number of universes, each with different physical constants. In this view, our universe appears fine-tuned for structure and life simply because we happen to exist in one of the rare universes where the constants allow for it. No designer needed, just probability across infinite trials. Andre Linde's eternal inflation models support this picture. The inflationary expansion continues globally, with bubble universes nucleating from the inflationary vacuum, each potentially with different constants. This sounds elegant, but examine what it actually claims. The multiverse theory proposes an infinite number of unobservable universes to explain the fine-tuning of the one universe we can observe. There is no experimental evidence for any other universe, no observation, no measurement, no detection. No instrument has been built or proposed that could observe another universe. The theory is not falsifiable. There is no possible observation that could prove it wrong. By the standards of the scientific method, observation, experimentation, falsifiability, reproducibility, the multiverse is not science. It is philosophical speculation dressed in scientific language. Even if we granted infinite universes, the problem is not solved but pushed back. Where did the multiverse come from? What mechanism generates these universes? Eternal inflation requires an inflaton field with specific potential energy properties. It requires quantum field theory. It requires general relativity. It requires the laws of physics. the mechanism that generates universes would itself require explanation and its own fine-tuning. The multiverse does not eliminate the need for a cause, it multiplies it. The multiverse is not an explanation, it is an escape route, an attempt to avoid the conclusion that fine-tuning implies a fine-tuner. But the escape fails. The evidence still points in one direction. The precise configuration of physical constants from a landscape of alternatives spanning 120 orders of magnitude was not an accident. It was a decision. And decision requires will, knowledge, and power. This brings us to the observational evidence, the instruments that measure the universe we actually inhabit, and that constrain what any origin model must match. The history of precision cosmology is a history of instruments, each one revealing with increasing clarity a universe with specific, quantifiable, fine-tuned properties. None of them has observed a creation event. None has detected nothing. Each has confirmed a universe of extraordinary structure, described by equations that assume a framework. Let us examine them in order. COBE, the Cosmic Background Explorer, was a NASA satellite that operated from 1989 to 1993. COBE carried 3 instruments designed to study the cosmic microwave background, the thermal radiation left over from the era, roughly 380,000 years after the Big Bang, when the universe cooled sufficiently for atoms to form and photons to travel freely. COBE confirmed that the CMB has a near-perfect black-body spectrum at a temperature of approximately 2.725 Kelvin, 2.725 degrees above absolute zero, or approximately negative 270.4 degrees Celsius, approximately negative 454.8 degrees Fahrenheit. This black-body spectrum is the most perfect thermal spectrum ever measured, deviating from a perfect Planck curve by less than 1 part in 10,000. The perfection of this spectrum is itself a datum. It confirms that the early universe was in thermal equilibrium to an extraordinary degree, consistent with a hot, dense early state. COBE also discovered tiny anisotropies in the CMB temperature, fluctuations of approximately 1 part in 100,000, or roughly 30 millionths of a Kelvin. These anisotropies represent density variations in the early universe, regions of slightly higher and slightly lower density that would eventually, over billions of years, collapse under gravity to form the galaxies and galaxy clusters we observe today. The anisotropies are consistent with the predictions of inflationary models, quantum fluctuations in the vacuum during the inflationary epoch, stretched to cosmological scales by the exponential expansion. COBE's discovery of these anisotropies earned John Mather and George Smoot the Nobel Prize in Physics in 2006. But the inflationary explanation, quantum fluctuations in a vacuum stretched by exponential expansion, requires a pre-existing vacuum energy, a pre-existing space-time, and a pre-existing framework of quantum field theory. The fluctuations are not fluctuations of nothing. They are fluctuations of something, a quantum field in its ground state, within the framework of established physics. WMAP, the Wilkinson Microwave Anisotropy Probe, was a NASA satellite that operated from 2001 to 2010. WMAP measured the CMB temperature fluctuations to higher angular resolution and precision than COBE, and extracted a wealth of cosmological parameters from the data. WMAP determined the age of the universe at approximately 13.77 billion years, roughly 4.35 times 10 to the 17 seconds, with a precision of approximately 0.3%. For perspective, if the entire cosmic history were compressed into one calendar year, the universe would begin at midnight on January 1st. The first atoms would form in the first week of January. The first galaxies would appear in late January. The Earth would form in early September, and all of recorded human history would occur in the final fraction of a second before midnight on December 31st. WMAP also determined the composition of the universe. Approximately 5% normal matter, the protons, neutrons, and electrons that make up atoms, molecules, stars, planets, and all visible structures. Approximately 27% dark matter, matter that does not interact with light, detected only through its gravitational effects on galaxies and galaxy clusters. And approximately 68% dark energy, vacuum energy, the cosmological constant, the energy density of empty space that drives the accelerating expansion of the universe. These percentages are not rough estimates. They are measured to percent-level precision from the angular power spectrum of the CMB, combined with other observations. And they describe a universe dominated by dark energy, by the very substance that physicists call empty space. 68% of the cosmos is vacuum energy. This is not nothing. This is the dominant component of the universe. The Planck satellite, an ESA mission that operated from 2009 to 2013, with final data released in 2018, provided the highest resolution map of the cosmic microwave background ever produced. Planck observed the CMB at 9 frequency bands, with angular resolution down to approximately 5 arc-minutes, and produced maps of the temperature and polarization of the CMB across the entire sky. Planck confirmed the flat geometry of space. The total density parameter omega sub tot equals 1.0007 plus or minus 0.0019, flat to within 0.2%. Planck refined the age to 13.80 plus or minus 0.02 billion years. The Hubble constant to approximately 67.4 kilometers per second per megaparsec, and the vacuum energy fraction, omega sub lambda, to approximately 0.685. The so-called Hubble tension, a discrepancy between the Planck-derived value of the Hubble constant, approximately 67.4, and local measurements using supernovae and Cepheid variables, approximately 73, remains an active area of research. Even the locally measured values still imply an expanding universe originating in a hot, dense state, a Big Bang. The tension does not change the fundamental picture. It refines the numbers. Any viable model of cosmic origin must match Planck's numbers. Age, 13.80 billion years. Geometry, flat. Composition, 5% matter, 27% dark matter, 68% dark energy. Hubble constant, 67.4 kilometers per second per megaparsec. These are the measured properties of the universe we inhabit. They are not negotiable. They are not approximate. And not one of them is nothing. The Large Hadron Collider, the LHC, is a 27-kilometer circumference proton-proton collider at CERN, straddling the Swiss-French border near Geneva. The LHC accelerates protons to energies of 6.5 TeV per beam, producing collisions at a center of mass energy of 13 TeV, the highest energy ever achieved in a laboratory. In 2012, the ATLAS and CMS experiments at the LHC discovered the Higgs boson, the particle associated with the Higgs field. The Higgs field is not an abstract concept. It is a quantum field that permeates all of space, with a measured vacuum expectation value of approximately 246 giga-electron volts. The Higgs field gives particles their masses through the mechanism of electroweak symmetry breaking, the process by which the W and Z bosons, the carriers of the weak nuclear force, acquire mass, and by which fermions acquire their rest masses through Yukawa couplings. The discovery of the Higgs boson confirmed that empty space is not empty. It contains a non-zero field, the Higgs field at its vacuum value, that interacts with every massive particle in the Standard Model. The LHC did not discover nothing. It discovered that what we call nothing contains a field with a specific, measured, non-zero value. LIGO, the Laser Interferometer Gravitational Wave Observatory, and its European counterpart, Virgo, began detecting gravitational waves in 2015. The first detection, two merging black holes, validated Einstein's general relativity in the strong gravity regime and opened an entirely new observational window on the universe. In 2017, LIGO and Virgo detected gravitational waves from a binary neutron-star merger, and electromagnetic observatories around the world detected the light from the same event, confirming that such mergers are sites of heavy element nucleosynthesis, the production of elements like gold, platinum, and uranium through rapid neutron capture. These observations confirm the framework, general relativity, nuclear physics, quantum field theory, within which every universe from nothing argument operates. The framework is not hypothetical, it is measured. It is confirmed by gravitational waves, by electromagnetic radiation, by the production of specific elements at specific sites. The framework is real, and the framework is not nothing. BICEP and the Keck Array, telescopes at the South Pole, have been searching for B-mode polarization in the cosmic microwave background. B-modes, produced by primordial gravitational waves, would be direct evidence for cosmic inflation, the exponential expansion driven by vacuum energy in the very early universe. In 2014, the BICEP-2 team announced a detection that was initially celebrated as confirmation of inflation. The signal was later attributed to thermal emission from galactic dust, not primordial gravitational waves. The retraction was a reminder of the difficulty of these measurements and the high standard of evidence required. As of the latest data, Only upper limits on the primordial B-mode signal exist. Inflation remains consistent with all observations, but is not directly confirmed. Forthcoming missions, including Lightbird and CMBS-4, will push the sensitivity further. Even if inflation is confirmed, it will confirm that a vacuum energy-driven exponential expansion occurred using a pre-existing vacuum field governed by pre-existing laws. It will not confirm creation from nothing. The James Webb Space Telescope, JWST, launched in December 2021, observes the universe in infrared at wavelengths from 0.6 to 28 micrometers. JWST has observed galaxies at redshifts greater than 10, galaxies forming 300 to 500 million years after the Big Bang, in the earliest epoch of cosmic structure formation. JWST provides data on the first stars, the first galaxies, and the chemical enrichment of the early intergalactic medium. ESA's Euclid satellite, launched in 2023, and NASA's Nancy Grace Roman Space Telescope, planned for 2027, will map dark matter and dark energy across billions of light years, refining our understanding of vacuum energy and its role in the expansion of the universe. None of these missions can observe what happened at t=0. None can peer behind the Big Bang. None can detect what existed or did not exist before space-time. The data constrains models. It does not answer the fundamental question. No instrument we possess or envision can observe the Planck epoch, the first approximately 5.39 times 10 to the negative 44 seconds after the Big Bang, where quantum gravity effects dominate. The Planck length is approximately 1.616 times 10 to the negative 35 meters, roughly 10 to the negative 20 times the diameter of a proton. The Planck density is approximately 5 times 10 to the 96 kilograms per cubic meter, a density so extreme that no known physics applies. We have no testable theory of quantum gravity. String theory, loop quantum gravity, and other approaches remain active research programs without experimental confirmation. Every statement about what happened at t=0 or before t=0, if the concept is meaningful, is a theoretical model, not an observation. George Ellis was clear. How indeed can you test what existed before the universe existed? You can't. This is not an expression of ignorance. It is a statement about the structural limits of empirical science. The origin of the framework lies beyond the framework's ability to observe itself. This brings us to the Friedmann equation in its general form. h squared equals 8 pi g over 3 times rho minus k c squared over a squared plus lambda over 3. A is the scale factor. K is the curvature parameter. Planck's measurement that omega sub tot approximately equals 1 means K approximately equals 0. The universe is flat. This flatness was one of the puzzles inflation was designed to solve. Without inflation, the initial conditions would require extraordinary fine-tuning. But inflation itself requires the Friedmann equation to hold, which requires general relativity, which requires space-time, which requires a metric, which requires mathematics. The chain runs backward from observation to law to framework. At no point does it terminate in nothing. The acceleration equation. A double dot over A equals negative 4 pi g over c squared over A equals negative 4 pi g over 3 times the quantity rho plus 3p over c squared plus lambda over 3. Only vacuum energy, with pressure P equals negative rho c squared, produces positive acceleration. Normal matter decelerates. Radiation decelerates. Dark energy accelerates. The observed accelerating expansion requires lambda to be non-zero, requires vacuum energy to exist. If there were truly nothing, no vacuum energy, no rho, no pressure, there would be no acceleration. There would be no expansion. There would be nothing. The Bekenstein-Hawking entropy. S equals K sub B times A over 4 L sub P squared. S is entropy. K sub B is Boltzmann's constant. A is the horizon area. L sub P is the Planck length. The entropy of the observable universe, estimated from the cosmological horizon, is enormous. If the universe appeared from nothing, where did all that entropy come from? Where did the information encoded in the boundary come from? The formula links gravity, quantum theory, and information in ways we do not understand. But the formula presupposes gravity and quantum theory. It does not derive them. Let us now examine the alternative models and assess what they actually explain, and, more importantly, what they assume. The steady-state theory, proposed by Hermann Bondi, Thomas Gold, and Fred Hoyle in 1948, offered an alternative cosmology in which the universe is eternal and unchanging on large scales. In the steady-state model, new matter is continuously created as the universe expands, maintaining a constant average density despite the expansion. The theory was elegant in one respect. It avoided the need for a beginning entirely. If the universe is eternal, the question what came before does not arise. There is no before. There is only an infinite past. The steady-state model was largely abandoned after the discovery of the cosmic microwave background in 1965 by Arno Penzias and Robert Wilson. The CMB is a relic of a hot, dense, early state, exactly as the Big Bang model predicted. An eternal, unchanging universe would not produce such a relic. The CMB was the decisive evidence. The universe had a history. It was hotter in the past. It was denser in the past. It had a beginning, or at least a state dramatically different from the present. The steady-state model failed the observational test. But it serves a historical purpose in our examination. It demonstrates that the scientific community once seriously considered, and ultimately rejected, an eternal universe as an alternative to a universe with a beginning. The idea of an eternal cosmos is not absurd, it is simply contradicted by the data. Cyclic models, such as the ekpyrotic model proposed by Paul Steinhardt and Neil Turok, offer a different approach. These models propose an endless series of expansions and contractions, or brane collisions in higher dimensional spacetime, replacing a singular beginning with an infinite cycle of cosmic phases. In the ekpyrotic scenario, two branes, extended objects in a higher dimensional space, collide periodically, with each collision producing a Big Bang-like event that reheats the universe and starts a new cycle of expansion, cooling, structure formation, and eventual contraction. The universe has no singular beginning. It cycles through phases, each producing the conditions for the next. Cyclic models can explain the homogeneity and flatness of the universe without requiring inflation. The collision geometry naturally produces a smooth, flat initial state. But they require new physics that has not been observed. Extra spatial dimensions, brane dynamics, and energy conditions that may violate known constraints. No observational evidence distinguishes cyclic models from standard inflationary cosmology. They remain theoretical constructions of research interest, but without empirical confirmation. Critically, cyclic models do not derive the universe from nothing. They propose that something has always existed, cycling through phases, with each phase governed by the laws of physics operating in a higher dimensional space-time. The framework, the extra dimensions, the branes, the physical laws, is eternal in these models. The question, where did the framework come from, is not answered. It is assumed away by positing eternity. Alan Guth, born 1947, American physicist at MIT, introduced cosmic inflation in 1980. Guth's key insight was that a false vacuum, a higher energy vacuum state, metastable and decaying, could drive a brief but extraordinarily rapid exponential expansion of space. This expansion would solve three long-standing problems in standard Big Bang cosmology. The horizon problem, why the CMB temperature is so uniform across regions of the sky that were never in causal contact, regions so far apart that light has not had time to travel between them since the Big Bang. The flatness problem, why the spatial geometry of the universe is so extraordinarily close to flat, omega approximately equals 1, when the slightest deviation early on would have been amplified by the subsequent expansion. And the monopole problem, why magnetic monopoles, exotic particles predicted by grand unified theories, are not observed in abundance. Inflation solved all three problems with a single mechanism. A brief period of exponential expansion driven by the potential energy of a scalar field, the inflaton, in a false vacuum state. The expansion stretched any initial curvature to flatness, diluted any monopoles to undetectable densities, and brought distant regions into causal contact before inflating them apart. The tiny quantum fluctuations in the inflaton field during inflation were stretched to macroscopic scales, becoming the density perturbations that would seed the formation of galaxies and galaxy clusters. The predictions of inflation, flat geometry, nearly scale-invariant density perturbations, Gaussian statistics of the fluctuations are consistent with all CMB observations from COBE, WMAP, and Planck. Inflation is a successful theoretical framework. Inflation, though, requires inputs. It requires a scalar field, the inflaton, with a specific potential energy function. It requires the mathematical framework of quantum field theory to describe the inflaton's dynamics. It requires general relativity to describe the expansion of spacetime. It requires the pre-existence of spacetime itself, a spacetime that can expand. Inflation does not derive these from nothing, it assumes them. The false vacuum that drives inflation is a state of pre-existing fields, not a state of non-existence. The decay of the false vacuum to the true vacuum releases energy that reheats the universe and produces the particles we observe. The entire process is a phase transition within a framework, a transition governed by laws, described by equations, occurring in space-time. It is not creation from nothing. Andrei Linde, born 1948, Russian-American physicist at Stanford, developed several variants of inflation, including new inflation, chaotic inflation, and eternal inflation. In chaotic inflation, the inflaton field can take any initial value at different points in space, with regions of high potential energy inflating exponentially, while regions of low potential energy do not. In eternal inflation, the inflationary expansion never ends globally. It continues in some regions of space-time even as others exit inflation and form distinct bubble universes. This leads to the multiverse hypothesis, an ensemble of bubble universes, each nucleating from the inflationary vacuum, each potentially with different effective physical constants as the inflaton field settles into different vacuum states. Linde's work is important for the multiverse discussion, which we have already examined and found wanting. But his work also underscores a deeper point. Even the most expansive version of inflation, eternal inflation, producing an infinite number of bubble universes, assumes the pre-existence of the inflaton field, quantum field theory, general relativity, and space-time. The multiverse, if it exists, is produced by a pre-existing framework. It is not produced from nothing. The framework generates universes. The framework itself is unexplained. Edward Tryon's 1973 proposal, the zero-energy universe, deserves revisiting in this context. Tryon suggested that the universe is a vacuum fluctuation that has persisted because its total energy is zero. The positive mass energy of matter and radiation is exactly balanced by the negative gravitational potential energy, yielding net zero. In this picture, the universe is not a violation of energy conservation, it is a zero-energy state that has separated from the vacuum and expanded. The idea is mathematically coherent within the framework of general relativity, where global energy conservation is subtle, and the total energy of a spatially flat universe is often said to be zero or undefined. The zero-energy universe hypothesis, as we have examined, does not solve the fundamental problem. Even if the total energy is zero, the bookkeeping requires entries: mass energy fields on one side, gravitational potential energy on the other, and the laws of general relativity to relate them. The balance is achieved within a framework. The framework is not derived from the balance, it is presupposed by it. Here is the pattern. Inflation assumes fields and laws. The multiverse assumes inflation. Vilenkin's tunneling assumes quantum gravity. Hartle-Hawking assumes Euclidean path integrals and the laws of physics. Krauss assumes the quantum vacuum. Hawking assumes a law such as gravity. Tryon assumes energy conservation in general relativity. Every model assumes a framework. Not one derives the framework from nothing. The chain of explanation runs backward, and at every step It requires something to already exist. The chain does not terminate in nothing. It terminates in an assumed framework that no model explains. The materialist might respond, "We don't know yet. Science will eventually explain it." Let us examine this response with the same rigor we have applied to every other claim in this video. "We don't know yet, but science will figure it out," is not an argument. It is a statement of faith. Faith in the capacity of future scientific discoveries to resolve a question that may lie beyond the scope of science itself. It is the secular equivalent of "God works in mysterious ways," a placeholder for an explanation that does not exist, deployed to avoid a conclusion the speaker finds uncomfortable. It has no evidence behind it. It makes no testable prediction. It offers no mechanism. It is an expression of confidence in a future that may never arrive. Consider the structure of the claim. The materialist is saying, "The evidence currently points toward a creator, but I believe that future evidence will point away from a creator." This is not following the evidence. This is rejecting the evidence in favor of a hoped-for alternative. It is the mirror image of the God of the gaps accusation that atheists frequently level against theists. The theist is accused of saying, "I don't understand X, therefore God did it." But the materialist is doing exactly the same thing in reverse. "I don't have an alternative explanation, therefore science will eventually provide one." This is a science of the gaps, a faith commitment to the future explanatory power of an enterprise that, by its own structure, may be incapable of answering the question at hand. There is a structural reason it may be incapable. Science describes how a system operates. It describes the dynamics of fields, the development of space-time, the expansion of the universe according to equations. The scientific method operates within a framework. It assumes the existence of natural laws, proposes hypotheses about those laws, tests the hypotheses through observation and experiment, and refines the hypotheses based on the results. The method is extraordinarily powerful for describing the behavior of systems that already exist. It is, by its nature, incapable of explaining why the system exists in the first place. The Friedmann equation describes how rho and lambda determine H. It does not explain why rho and lambda exist. The Schrödinger equation describes how the wave function evolves in time. It does not explain why there is a wave function. Maxwell's equations describe how electric and magnetic fields propagate and interact. They do not explain why electromagnetic fields exist. The Standard Model of Particle Physics describes the interactions of 17 particles and 4 fundamental forces with a precision that matches experiment to extraordinary accuracy. It does not explain why those 17 particles exist, why those 4 forces have the strengths they do, or why the mathematical framework of quantum field theory applies to reality at all. Emmy Noether's theorem, one of the deepest results in mathematical physics, establishes a deep connection between symmetries and conservation laws. Time translation symmetry yields conservation of energy. Spatial translation symmetry yields conservation of momentum. Rotational symmetry yields conservation of angular momentum. The theorem is beautiful, rigorous, and consequential. It describes relationships within a system, relationships between the symmetries of a Lagrangian, and the conserved quantities of the dynamics. But the theorem requires a Lagrangian. It requires the variational principle. It requires continuous symmetries. It requires the mathematical framework of analytical mechanics. Noether's theorem does not explain why the Lagrangian has the form it does. It does not explain why variational principles hold. It does not explain why symmetries exist. It describes what follows from symmetries. It does not explain why there are symmetries to follow from. The question, why is there something rather than nothing, is not a scientific question in the strict sense. It is a metaphysical question, a question about the existence of the framework within which science operates. And no equation within the framework can answer a question about why the framework exists. An equation cannot justify its own existence. A law cannot explain why it holds. A conservation principle cannot explain why there is anything to be conserved. The question transcends physics, not because physics is defective, but because physics has a defined scope, and this question lies beyond it. Richard Feynman, the Nobel laureate, one of the architects of quantum electrodynamics, once stated, "I think I can safely say that nobody understands quantum mechanics." This is not a confession of ignorance about how to use quantum mechanics. Feynman was one of the most skilled calculators in the history of physics. It is an acknowledgement that the formalism works, it predicts experimental results with extraordinary precision, without anyone understanding why it works, or what it means at the deepest level. The equations produce correct answers. The physical picture behind the equations remains contested after nearly a century of debate. The measurement problem, the collapse of the wave function, the ontological status of superposition, these are not technical problems awaiting better instruments. They are conceptual puzzles that the formalism itself does not resolve. This candid admission from the heart of physics carries weight for our topic. If the most successful physical theory in human history, quantum mechanics, is not fully understood even by its greatest practitioners, then the confidence with which some physicists pronounce on the ultimate origin of the universe should be tempered. The equations work within the framework. The equations do not explain the framework. And the claim that future equations will explain the framework is an article of faith, not a conclusion from evidence. I return to this point often, not because it is comfortable, because it is true. The most fundamental question a conscious being can ask, why is there something rather than nothing, is precisely the question that the most successful physical theories in human history cannot answer. Not because we have not found the right equation yet, because the question is about the existence of equations themselves, and no equation can explain why equations exist. The question is metaphysical. The answer, if there is one, is metaphysical. And the metaphysical answer that best fits the evidence, power, knowledge, will, eternality, independence, is the existence of a creator. Some might say this is not a scientific conclusion. They are right. It is not. It is a philosophical conclusion, drawn from the limits of science combined with the evidence science has produced. Science tells us the universe is 13.8 billion years old, that its constants are fine-tuned to 1 part in 10 to the 120, that its vacuum is filled with fields and energy, that its expansion is described by the Friedmann equation, and that its structure was seeded by quantum fluctuations in a pre-existing vacuum. Science does not tell us why any of this exists. Philosophy must take over where science reaches its limit. And when philosophy examines the evidence, the fine-tuning, the mathematical order, the existence of consciousness, the impossibility of something from nothing, the conclusion is not ambiguous. The evidence points to a creator. Now let us follow the evidence where it leads. Something has always existed. This is not a matter of belief, it is a matter of logic. If there were ever truly nothing, absolute nothing, with no fields, no energy, no laws, no potential, no space-time, no mathematical structure, then nothing would exist now. Nothing has no mechanism. Nothing has no capacity. Nothing has no tendency. Nothing has no laws governing what it can or cannot produce, because there are no laws. Nothing has no quantum fields to fluctuate, because there are no fields. Nothing has no uncertainty principle to allow brief energy violations, because there is no energy, no time, and no principle. Nothing does not fluctuate. Nothing does not tunnel. Nothing does not nucleate. Nothing does nothing. 0 plus 0 equals 0, and it always equals 0. No amount of time changes this, because in absolute nothing, there is no time. We exist, though. The universe exists. The quantum vacuum exists. The laws of physics exist. The Friedmann equation describes a real expansion. The Hubble constant measures a real recession. The CMB is a real thermal relic at 2.725 Kelvin. The Casimir effect produces a real force. The Higgs field has a real vacuum expectation value of 246 giga-electron volts. Therefore, something has always existed. Not probably, not perhaps, necessarily. The existence of anything now logically requires the eternal existence of something. The question is, what is this eternal something? Option 1, the materialist answer. Matter, energy, or the quantum vacuum. Something unconscious, purposeless, and undirected has always existed. And through blind, unguided processes, quantum fluctuations, gravitational collapse, nuclear fusion, chemical reactions, produced the universe we observe. A universe with mathematical laws. A universe with physical constants fine-tuned to 1 part in 10 to the 120. A universe with conscious observers who ask why they exist. A universe describable by equations of extraordinary precision and elegance. All of this, according to materialism, arose from unconscious, purposeless, undirected stuff. Let us examine this answer with the same rigor we applied to Krauss and Hawking. If the eternal something is unconscious matter or energy, then unconscious matter produced a universe with mathematical order. The Friedmann equation describes the expansion of space-time with a precision confirmed by Planck to fractions of a percent. The standard model of particle physics describes the interactions of 17 particles and 4 forces, with a precision that matches experiment to 10 or more significant figures. The fine structure constant, 1/137.036, determines the strength of every electromagnetic interaction in the universe, and its value permits the existence of stable atoms, complex chemistry, and the entire periodic table. Unconscious matter, according to materialism, produced this mathematical order without intending to, without knowing mathematics, without possessing the concept of order. The claim is extraordinary, and extraordinary claims require extraordinary evidence. The materialist has none. What the materialist has is a commitment to a philosophical position, naturalism, and a determination to interpret all evidence within that framework, regardless of where the evidence actually points. If the eternal something is unconscious, then unconscious matter produced the cosmological constant at a value of 6 × 10⁻27 kilograms per cubic meter, a precision of 1 part in 10 to the 120, by accident, by chance, by an unguided process that happened to select from a landscape of 10 to the 120 alternatives the one value that permits structure. Think about that number. Now ask yourself, could this be accidental? Could an unconscious process with no knowledge of the outcomes, with no preference for structure over formlessness, with no intention of any kind, produce a result fine-tuned to 1 part in 10 to the 120? The question answers itself. The probability is so small that it is, for all practical and philosophical purposes, 0. And it happened by chance is not an explanation when the probability approaches 0. It is a refusal to accept the obvious. If the eternal something is unconscious, then unconscious matter produced conscious beings. This is the hard problem of consciousness, identified by philosopher David Chalmers and acknowledged as unsolved by the entirety of the neuroscience community. Atoms have no awareness. Molecules have no thoughts. Neurons fire electrical signals, but the transition from electrical signals to subjective experience, the what it is like to see red, to feel pain, to think a thought, has no materialist explanation. Neuroscience can correlate brain states with mental states. It can identify which brain regions are active during specific experiences. But correlation is not explanation. The question is not where consciousness correlates in the brain. The question is how physical processes, which are, at bottom, arrangements of electrons, protons and neutrons, obeying the equations of quantum mechanics and electrodynamics, give rise to subjective first-person experience. No materialist theory has answered this question. Not functionalism, not computationalism, not emergentism, not physicalism in any of its variants. The hard problem remains hard, and the materialist claim that mind arose from mindless matter through unguided processes is not a conclusion drawn from evidence. It is a philosophical commitment that the evidence does not support. When I first understood this, that the most successful physical theories in human history cannot explain consciousness, cannot explain the fine-tuning, cannot explain why the laws exist, the materialist framework I had accepted as default began to look less like a conclusion from evidence and more like an assumption protected from examination. The evidence was pointing somewhere. I had been trained not to look. Option 2. The alternative. The eternal something is not unconscious. It is not purposeless. It is not undirected. It possesses the attributes that the evidence requires. Power sufficient to bring a universe into existence. The total mass energy of the observable universe is approximately 1.5 times 10 to the 53 kilograms, or equivalently, approximately 10 to the 70 joules. Whatever caused the universe possesses power on this scale and beyond, because the cause must be external to the system it created, and therefore not bound by the system's energy constraints. Knowledge, sufficient to configure physical constants to the precision of 1 part in 10 to the 120. The cosmological constant, the fine structure constant, the gravitational constant, the mass ratios of fundamental particles, each is set to a value that permits structure, chemistry, and complexity. The configuration is not random. It is specific. Specificity from a vast landscape implies knowledge of the landscape and of the consequences of each setting. Will, because a specific configuration was selected from an infinite landscape of alternatives. Selection is an act. Acts require agents. Agents that select possess will. The universe could have had different constants. It could have had no constants. It could have had no laws. The fact that it has one specific configuration, the one that permits complexity, implies that a choice was made. And choice requires a chooser. Eternality, because the cause of the universe must be external to time. Time began with the Big Bang, or at the very least, our physical models of time break down at the Planck epoch. Whatever caused the universe exists outside of time. It is not subject to temporal beginning or end. It is eternal. Independence, because the cause cannot depend on the universe it created. The laws of physics describe the behavior of the universe. The cause of the universe is not subject to the laws of the universe, because those laws are among the things that require a cause. The cause is independent of its effects. These are exactly the attributes that every civilization in human history has ascribed to a creator. Power, knowledge, will, eternality, independence. This is not a coincidence. It is a convergence of evidence and intuition, a convergence that spans cultures, centuries, and continents. The infinite regress argument reinforces this conclusion. If every cause requires a prior cause, stretching backward infinitely, then nothing would ever begin. An infinite chain of dependent causes, each one depending on the one before it, with no first link, would never reach the present. The present would require an infinite number of prior events to have occurred, which is logically impossible for a series with no beginning. The fact that we exist, that the present moment is real, that the universe is here, that the CMB is measurable at 2.725 Kelvin, that galaxies recede at 67.6 kilometers per second per megaparsec, proves that the chain of causes terminates. Something exists that is itself uncaused. Something eternal, self-sufficient, independent. The chain cannot extend infinitely backward. It must have a first link, an uncaused cause. Asking who created the creator is a misunderstanding. The argument does not claim that everything has a cause. It claims that everything that begins to exist has a cause. The creator, by definition, did not begin to exist. The creator is eternal, the termination point of the causal chain. Something must always have existed. The materialist accepts this implicitly when they propose that matter, energy, or the quantum vacuum is eternal and uncaused. They have already accepted the concept of an eternal, uncaused something. The only remaining question is the nature of that something. Is it unconscious matter, blind, purposeless, undirected? Or is it an intelligent creator with power, knowledge, and will? The evidence, fine-tuning at 1 part in 10 to the 120, mathematical order describable by equations of extraordinary precision, the existence of conscious observers in a universe of unconscious particles, points to intelligence. The conclusion is not mysterious, it is rational. Let us now assemble the full evidence file, every datum, every equation, every observation, every argument, and state the conclusion plainly. The quantum vacuum is not nothing. It is the lowest energy state of quantum fields, an infinite collection of oscillators, each carrying a minimum energy of 1/2 h bar omega, as required by the Heisenberg uncertainty principle and confirmed by the Casimir effect, predicted by Hendrik Casimir in 1948, measured by Steve Lamoureux in 1997 at 1.3 times 10 to the negative 7 newtons per square meter, at 1 micrometer separation. The Lamb shift, measured by Willis Lamb in 1947, and the anomalous magnetic moment of the electron. Virtual particles are excitations of pre-existing fields governed by pre-existing laws, not creations from non-existence. The quantum vacuum has properties, dynamics, and measurable energy. It is a physical state, a state of something, not of nothing. Calling it nothing is a redefinition identified as such by George Ellis. He does not explain why the pre-existing fields should have existed at all. Krauss does not address why the laws of physics exist. David Albert: none of these poppings amount to anything even remotely in the neighborhood of a creation from nothing. And John Horgan: none of these poppings amount to anything of a creation from nothing. Sean Carroll's summary captures it. The vacuum is infused with the potential to be anything. Potential is a property of something, not of nothing. The claims of Krauss, Hawking, Vilenkin, and others that the universe arose from nothing fail on their own terms, examined, tested, and found wanting. Krauss's nothing is a quantum vacuum with fields, energy, and physical laws. His own statement, "Nothing is every bit as physical as something," concedes the redefinition. The prosecution rests on his own words. Hawking's claim, because there is a law such as gravity, the universe can and will create itself from nothing, begins by assuming a law exists, the Einstein field equations, the gravitational constant g, the speed of light c, the mathematical apparatus of differential geometry on a Lorentzian manifold. The argument undermines its own premise. Vilenkin's tunneling from nothing requires the Wheeler-DeWitt equation, quantum gravity boundary conditions, a tunneling probability, a wave function, and the framework of quantum cosmology. Hartle-Hawking's no-boundary proposal requires Euclidean path integrals, a Lagrangian, and the laws of physics. Tryon's zero-energy universe requires energy conservation within general relativity, which requires general relativity to exist. Not one of these models derives the framework from nothing. Each assumes the framework and operates within it. The nothing in each case is a technical term for a specific physical state within a pre-existing system. True nothing, philosophical nothing, absolute nothing, has no fields, no energy, no laws, no space-time, no mathematical structure, and no potential for fluctuation. From true nothing, nothing comes. The prosecution against universe from nothing is complete. Every equation in cosmology requires inputs that are not nothing. The Friedmann equation, h² equals 8 pi g over 3 times rho plus lambda over 3, requires energy density rho, vacuum energy lambda, and the gravitational constant g, derived by Alexander Friedmann in 1922 from Einstein's field equations. The Hubble law, V equals h sub 0 d, requires spacetime, distances, and the framework of general relativity, first observed by Edwin Hubble in 1929. The Heisenberg uncertainty principle, delta E delta T greater than or equal to h bar over 2, formulated by Werner Heisenberg in 1927, requires quantum mechanics, energy, and time. The zero-point energy formula, E sub min equals 1/2 h bar omega, establishes that even the lowest state of any quantum field has non-zero energy, traced to Max Planck's 1911 introduction of zero-point energy. The cosmological constant relation, rho sub lambda equals lambda c squared over 8 pi g, connects vacuum energy to the accelerating expansion, derived from Einstein's field equations, first introduced with the cosmological constant in 1917. The Friedmann acceleration equation, a double dot over a equals negative 4 pi g over 3 times rho plus 3p over c squared plus lambda over 3, shows that only vacuum energy drives positive acceleration. Normal matter and radiation decelerate. The Bekenstein-Hawking entropy formula, S equals K sub BA over 4L sub P squared, attributed to Jacob Bekenstein in 1973 and Stephen Hawking in 1975, implies enormous information content at any cosmological horizon. Einstein's mass-energy equivalence, E equals mc squared, 1905, relates the observable universe's mass, approximately 1.5 times 10 to the 53 kilograms, to approximately 10 to the 70 joules. The Schwarzschild radius, r sub s equals 2 gm over c squared, Carl Schwarzschild, 1916, underpins black hole physics and Hawking radiation. None of these equations operates from nothing. None derives its framework from nothing. Each describes dynamics within a pre-existing system. Every model of cosmic origin assumes a pre-existing framework. Krauss's vacuum fluctuation assumes a quantum vacuum. Tryon's zero-energy universe, 1973, assumes energy conservation within general relativity. Guth's cosmic inflation, 1980, assumes a scalar field with a specific potential, governed by quantum field theory and general relativity. Lindy's eternal inflation assumes the inflaton field and the framework of quantum cosmology. Vilenkin's tunneling from nothing, 1982, assumes the Wheeler-DeWitt equation and quantum gravity boundary conditions. Hartle-Hawking's no-boundary proposal, 1983, assumes Euclidean path integrals and the laws of physics. Steinhardt and Turok's cyclic models assume extra dimensions, brain dynamics, and new physics. The steady-state model, Bondi, Gold, Hoyle, 1948, assumed continuous matter creation and was abandoned after the 1965 CMB discovery. Not one of these models derives the framework from nothing. The chain of explanation terminates, in every case, at a pre-existing framework that is assumed, not explained. The observational evidence, 7 decades of precision cosmology, describes a universe with specific, quantifiable, fine-tuned properties. Kobe, NASA 1989 to 1993, discovered CMB anisotropies at 1 part in 10 to the 5 and confirmed the black body spectrum at 2.725 Kelvin. WMAP, NASA 2001-2010, determined age 13.77 billion years. Composition 5% normal matter, 27% dark matter, 68% dark energy. The Planck satellite, ESA 2009-2013, final data 2018, confirmed flat geometry. Omega sub tot equals 1.0007 plus or minus 0.0019. Age 13.80 plus or minus 0.02 billion years. Hubble constant 67.4 kilometers per second per megaparsec. Dark energy fraction 0.685. The Large Hadron Collider, CERN, 2008 present, 13 TeV, discovered the Higgs boson in 2012, confirming the Higgs field with a non-zero vacuum expectation value of 246 giga-electron volts, proving that empty space contains a non-zero field. LIGO and Virgo, 2015 to present, detected gravitational waves from merging compact objects, validating general relativity in the strong gravity regime. The 2017 neutron-star merger confirmed heavy element nucleosynthesis. JWST, launched December 2021, observes galaxies at redshifts greater than 10. BICEP and Keck array search for B-mode polarization as evidence for inflation. Current data shows only upper limits. Euclid, ESA 2023, and the Nancy Grace Roman Space Telescope, NASA, planned 2027, will map dark energy properties. None of these instruments can observe the Planck epoch, approximately 5.39 times 10 to the negative 44 seconds, Planck length approximately 1.616 times 10 to the negative 35 meters. Every datum from every instrument confirms a structured, law-governed, fine-tuned cosmos, not nothing. The cosmological constant is fine-tuned to 1 part in 10 to the 120. This exemplifies the anthropic principle, the observation that the universe's properties appear precisely calibrated for the existence of observers. The fine structure constant is approximately 1/137. The gravitational constant, the strong nuclear coupling, the proton-to-electron mass ratio, each contributes to a narrow window of parameters permitting structure, chemistry, and complexity. The multiverse, proposed by some as an alternative explanation, has zero observational evidence, is unfalsifiable by the standards of the scientific method, and does not solve the problem, but pushes it to the mechanism generating universes, which itself requires explanation and fine-tuning. The "science will eventually explain it" response is a faith commitment, not an argument from evidence, and it fails to address the structural limitation that physics describes dynamics within a framework, but cannot explain why the framework exists. The chain of causes must terminate. An infinite regress of dependent causes would never reach the present. The existence of the present proves the chain has a first link, an uncaused cause, eternal, self-sufficient, independent. The materialist accepts this concept when positing eternal matter or energy. The question is the nature of the eternal something. The evidence demands specific attributes of the eternal something. Power sufficient to create 10 to the 70 joules of mass energy. Knowledge sufficient to configure constants to 1 part in 10 to the 120. Will, because a specific configuration was selected from an infinite landscape. Eternality, because the cause preceded time. Independence, because the cause is not subject to the laws it configured. These are not speculative. They are deduced from the evidence. And they are the attributes of a creator, recognized by every civilization in human history. Quantum fields, vacuum energy, the Casimir effect, the Friedmann equation, the Heisenberg uncertainty principle, the cosmological constant at 6 times 10 to the negative 27 kilograms per cubic meter, the fine structure constant at 1/137, the anthropic principle, the Higgs field at 246 giga-electron volts, COBE, WMAP, Planck, the LHC, LIGO, JWST. 13.8 billion years of cosmic history. 120 orders of magnitude of fine-tuning. 10 equations, 7 instruments, 12 physicists and philosophers. One question: why is there something rather than nothing? The most successful physical theories in human history cannot answer it. The equations describe a universe of extraordinary precision, mathematical elegance, and structured complexity. And they leave the most fundamental question unanswered: unless you follow the evidence where it leads. The universe did not come from nothing. Nothing comes from nothing. The quantum vacuum is not nothing. It is the quietest state of a structured, law-governed system. Every model of cosmic origin assumes a framework. Every equation requires inputs. Every observation confirms a universe with specific, fine-tuned properties. The materialist explanations have been examined fairly, rigorously, and on their own terms. They fail not because the physics is wrong, but because the physics assumes what it cannot explain. The physics is precise. The physics is confirmed. And the physics presupposes a framework whose existence it cannot account for. The evidence does not point to accident. It does not point to randomness. It does not point to unconscious matter producing conscious observers through blind processes across infinite time. The evidence points to an intelligent, powerful, eternal creator, one who existed before time and space, who configured the constants with knowledge, who chose this universe from the infinite alternatives with will. That is not faith against evidence. That is the conclusion the evidence demands when examined honestly. That conclusion, once reached, changes everything. Good night.